So 6.4, D is in Delta, college algebra, continuing on with polynomial equations. We're over at the fundamental theorem of algebra. And the fundamental theorem of algebra basically says if we have f of x and it's a polynomial, okay, just like we worked on with example 4, that was a polynomial. And if it has a degree greater than 1. So if it's like x to the 4th plus 3x cubed plus 2x squared plus 3x minus 1, and this number is greater than or equal to 1, then our answer, our y, our f of x, has at least one complex 0. It has at least one answer that is complex or is imaginary. Okay, so as a result, complex zeros, there's going to be, basically if there's one, you're going to really have two, because you're going to have this, and if you have it written in this form, you're also going to have it written in this form. Okay? Now, notice that 3 plus 0i equals 3. This can be written as a complex fraction, so that's why I say there is at least one complex 0, because 3 can be written that way. So anyway, not really a big deal at this point if you understand the whole fundamental theorem of algebra, as long as you understand how to use it. And that's what we're going to do here in example 5, and then look and see what's going on with the homework. So example 5, we have an equation that looks like this. Okay, and if we use our P over Q, we know that we're going to take those over, there's only the number 1 in front of here, so that's why it only looks like that. So that makes it easier. So there aren't a whole lot of opportunities for the numbers we're going to get. And if we graph this equation here, which is what I would suggest doing, you're going to get a graph where it looks like x crosses at the 1. Okay, and notice that's one of our options here, 1 over 1. Okay, so that's nice that works, but we don't know for sure, so of course we're going to do a real quick synthetic division here. But one of the things I want you to notice as I just did this is that I almost made a major mistake here. Remember that these have to be in numerical descending order. I have to have an x there. I can't just go from x squared to 3. Okay, so now 1, 2, 0, negative 3. I've got to remember to do that. I almost didn't. Okay, so x minus 1 works, leaving me with x squared plus 3x plus 3. Okay, so this is an x minus 1 when that's all factored down. And so obviously what makes that 0 is our 1. So I know one of my answers is 1. And my other ones are going to be whatever that factors down to. Now, when you factor this down using the quadratic formula, because it's not going to factor down, you're going to get negative 3 plus or minus the square root of negative 3 all over 2, which this negative here needs to come out. Negative 3 plus or minus I square root of 3 all over 2. And again, we have to put this, because it's imaginary, we have to put this in the form a plus bi. So we're going to have to pull these apart. So we've got negative 3 halves plus or minus I square root of 3 over 2. Okay, so that is going to be our answer. And notice that we have this showed up in pairs, negative 3/2 plus this and minus this. So we've got the conjugates here, like we had mentioned in the complex zeros of the fundamental theorem of algebra, bottom of page 474. Now, because we know we have 3 solutions, we have 2 here, plus this, minus this, and the 1 that we had over here, we know we're done. Okay, we know that we found all of them. Okay, so that is it for 6.4, and let's kind of look real quickly at what we have here in the homework using synthetic division for 1 through 4. In 5 and 6, you're trying to figure out whether the number they give you at the end of the semicolon, so in 5, the number there at the end is a 3. They want to know if that is a solution. So you do synthetic division, see if you get a remainder. If you do not get a remainder, then yes, it's a solution. And, same with 7 and 8, only you're using negative 3 because you've got x plus 3, so whatever makes that x plus 3 0, which is a negative 3, that's what you're going to use. Okay, pretty much everything else seems self-explanatory here. Find all rational zeros of the polynomial function, 21 to 24. I would just get my graphing calculator out, find one, use synthetic division to make sure it works, and then see if there are any other rational zeros. So again, rational zeros. They're not interested in the irrational numbers. The crazy numbers like this are not interested in. They're just interested in the 1s and 2s and the fractions. Okay. 25 to 30, they want all of them. Okay, just like what we did here. So you're going to end up using the quadratic formula in order to find these nasty looking ones. And then the exercises, the story problems, pretty much typical ones. They give you the formula and you're just finding the stuff that they want, just like in some of the other examples they gave us, like example 3. And that pretty much is it for 6.4.